think it's recording now.
Yeah, it is. It is. Okay, great. So let's go ahead and dive in. We're going to start today. Can you guys see this whiteboard?
Yep, we
Yep.
can.
Yep.
Okay. Is that the only thing that I'm sharing right now?
Yes.
Yes.
Yeah.
Okay, great. Okay, so what we're going to do is this is like our first lecture where we're going to get into the method, get into the finite element method. And our objectives are as follows. What we want to accomplish is we want to leverage smooth splines, for the following purposes. One, we want to increase accuracy and robustness in computed solutions. So kind of per degree of freedom. And two, we want to dramatically simplify model building. Those are our objectives. So in traditional FEA, in case you're not familiar with how it works, generally somebody builds some CAD, let's call this our CAD computer-aided design. This CAD object can be of any complexity, and this CAD object is not suitable for simulation directly. So you go through a process called mesh generation, which has, you know, steps like, there's also things like cleanup in here where you clean the CAD up and so on, to generate basically a new geometry now that has a mesh on it. And this process has become a huge bottleneck. Huge bottleneck in the CAD CAE pipeline. So just so you know, CAE, computer-aided engineering, is sometimes used synonymously with FEA, except it also encompasses things like CFD too. But I will use CAE and FEA somewhat interchangeably. So this process of converting CAD data into simulation data can account for, you know, greater than 90%, in particular for just get an eraser here. My eraser, where is it? In particular for complex simulations, whether they're multi-physics or they have complex geometry or both, many of the people that we work with spend more than 90% of their time in the process of converting CAD data into simulation data. It's not at all uncommon for simulations to run in the order of hours to days, and model preparation runs in the orders of weeks to months, which is really becoming even worse as industry becomes more reliant on simulation. So our objectives are to leverage the fundamental properties of smooth splines to build methods, finite element methods, that fundamentally impact number one and number two. And so we're going to start deriving a method today in 1D that has all the features that we're going to leverage in multi-dimensions to accomplish this objective. Okay, any questions on the high-level purpose or marching orders? Okay. All right, so let's begin. Let's pose a problem. And let's pose the simplest problem that we can think of. How about an elastic bar? Okay, we've got our bar here made out of some homogeneous isotropic material. Let's say that the coordinate axes run through the centroid of the bar, right? So let's call this coordinate x. And let's characterize this bar now as, in terms of some material properties, let's say that the Young's modulus, E, is given, and the cross-sectional area, so the cross-section here, this is A, let's say that is given. And we want to model the tension or compression response of this bar. All right. Okay, so let's assume further that the deformations are very small. So small deformation. So that essentially what this means is we have what we would call a linear or a linearized problem. All the key relationships are going to be proportional through some constants. Now, let's begin our modeling by writing down the strain energy of this object. So the strain energy, let's call it pi, it's going to be a function of the displacement u and something we're going to call a Lagrange multiplier. And it's going to be equal to, in kind of more general terms, I want to introduce some notation here. The following integrals derivative of u with respect to x squared. Okay, so this integrand is often called strain energy density. Okay, so this is basically the energy of internal deformation. And let's add some now energies associated with the work done by external forces. Let's start with, and I'm gonna come back to these symbols in a moment. Over the boundary, let's enforce a constraint. And again, I'm going to be pretty detailed in my explanations here in a moment, so just hang on. So this is a Lagrange multiplier. It's going to be interpreted as a force. So we have a force times a distance integrated. Okay. So we're integrating something in terms of the work done by a force. And then let's add a body force to this problem. Let's say we've got, again, work displacement times a body force. And let's add some traction. Okay.
Dr. Scott, what are those bounds in that second integral? What is that symbol?
I'm going to explain that now.
Okay.
So if you come over now to our problem, let's label what this is. Omega C is the entire domain. So it is the volume occupied by this bar. That's what omega C is. The gamma CD is where is the boundary where we're going to apply a displacement constraint. So this is gamma dc, this left boundary. And then gamma hc is the right boundary where we're going to apply our traction force. Okay, so we're going to basically clamp the left end with some constraint on the displacement. Maybe we say the displacement is 0 on the left end. And then we have two kinds of external forcings. One is a traction that's going to be a vector acting through the centroid of the cross-section. In this case, in 1D, it's just an arrow pointing to the right, H sub L. And then we also, I wonder if I can change color here. Let's see. Zoom's got to up their game on my annotation tools here. Well, unless I am missing something, I don't see a way to change the color of my pen. Anybody seen anybody change the color of their pen in Skype or in Zoom? Give me a hint.
I usually use OneNote for all of my annotation stuff for that reason.
Yeah.
It's sometimes you can click on the format on your annotation tile. There's the format and it drops down to other colors.
Ah, thank
Because you should be able to change color.
That did it, Clint. Wow, there's a whole variety of things. Okay, so let's change the color to red for the body force F. Okay, so we have a body force here acting. It's going to be in units eventually, not yet, but it will eventually be in units of force per length. Otherwise, in general, it's force per volume, but this is our little F. Okay, so we have two external forcings and a constraint. We have the energy consumed by internal deformation, the strain energy. And so this whole thing should be equal to some, let me change my back. This kind of potential energy, pi, should be equal to some constant. Okay. So this is a very common starting point in structural mechanics, is you postulate some energy. And then we're going to start with this energy and derive a finite element method from this. Let me tell you for a moment what the superscript C, that C is going to stand for CAD. So what I'm saying here is that these domains, omega and gamma, are somehow coming from a CAD description. Okay, and in this case, it's like a trivial CAD description because it's a very simple bar. Okay, let's go ahead and reduce all of this down to a one-dimensional problem. This is a one-dimensional problem. So these integrals now, I can put concrete limits of integration on them because I know that this is a one-dimensional problem. Let's call the left end x equal to 0. And the right end, let's say, is x equal to L for the length. Okay, and let's rewrite these integrals now as 1/2. The body, it goes from 0 to L. U comma x EA U comma x d omega. Now, the next term, this is a boundary, but in 1D, a boundary is just a point. And so this point here corresponds to x equal to 0. So this is nothing more than taking this integrand and evaluating it at x equal to 0. Let's go ahead and do that. So it's lambda evaluated at 0. Our unknown displacement evaluated at 0 minus some given initial displacement, u0. Okay, that takes care of that guy. This guy, again, just a volume or a line integral now at this point. So 0 to L. UF. As we could even eraser. Dx, dx. And then this, again, the right boundary is nothing more than the point x equal to L. So we're going to, what am I doing? The opposite of what I'm saying. So this is just U evaluated at L, and then H sub L is to equal some constant. Okay, so there is the strain energy, like the total energy of an elastic bar. All right, and we've already kind of called out that there's something special about the CAD geometry. We're going to need to know where that is, because we're not going to have the tight coupling between our approximation geometry and our CAD geometry. That's one of the ways we're going to dramatically simplify model building up here. That's also another reason we introduced a Lagrange multiplier here. Okay, so these functions, so what's the given data? We're going to be given this, some initial displacement. Usually this would just be 0, which means we would just have a bar fixed on the left end. We'll be given a body force, F, and we'll be given a traction. And then we'll be given some material and cross-sectional properties. Okay, any questions on this first sheet here from anybody?
So I guess one question just with the boundary conditions, kind of with the gamma D and gamma H. So those integrals are they're just evaluated at one point.
Yeah.
Okay, and so that's why they don't have anything more than just that one.
Exactly. Yeah, this is, you know, the real problem, of course, isn't a line, but we've simplified the model to basically be posed just on the x-axis.
Right. So if you had like a 3D volume, you might apply like say a pressure. Like if you have like a pressure vessel or like a basketball, you have like a pressure on the inside of the basketball, and so then your gamma, in that case, might be like the surface of the basketball, but not the volume of it.
Mm-hmm. Yeah. In general, that would be a way to think about it. Okay, any questions? Please speak up. I'm gonna try and I'm gonna try and not be really kind of detailed here, but it's gonna be a lot.
Sorry, one more clarification. Oh, yeah. Go ahead, Eric.
U comma X is the derivative of the displacement, right?
Yep, that's correct.
Annotation, okay.
Yep.
And then HL, that's a force on the end of the bar
Yeah.
for this example?
Uh-huh.
Okay.
Yep.
So what's the difference between the body force F and HL?
This attraction force is applied on the boundary, and a body force can be considered to be, let me write this down if I can remember. I had a good way of describing this. A body force is the forces that a body experiences. Actually, let me say this a little different. The simplest term is forces at a distance. So the canonical case of a body force is gravity. So what is gravity? Well, gravity is a force that's generated, basically by the sun and a gravitational pull. The origin of the force is at a distance. And so we model it as though every particle in the body is experiencing the same force simultaneously because it's acting at such a far distance. Tractions are basically forces up close, and they act on the boundary of objects. So the canonical example of a traction force would be, so this is forces directly applied to boundaries. And the canonical guy is a pressure. So you can kind of see why then the body force is integrated over the entire body, because we're assuming every particle is experiencing gravity simultaneously, whereas tractions are applied at specific points on the boundary. Those are really in a mechanical system, those are the ways that you can input energy into a mechanical system.
Awesome, thank you.
Okay, great. Now, these guys, these are our unknowns that we're going to solve for. So I want to know, for example, maybe I want to know what is the displacement that generates minimum energy, right? A minimum energy state. Find the displacement field U and the Lagrange multiplier lambda that gives me a minimum energy state. And so what we want to do now is take the derivative, the variational derivative of pi with respect to U and lambda and set them equal to 0, right? Because that's going to give us a local minimum or maximum, and that will give us what's called the weak form, as we discussed before. So before, our problem was like really simple, but now it kind of is taking on a physical meaning, right? We given an energy and we want to solve for the fields, the displacement and Lagrange multiplier fields that minimize the energy. And so taking this derivative now should have some real significance to you, those of you who have been studying solids for a while. So
Dr. Scott, a quick question. When you're evaluating, so this would be your second and fourth integral, are you even evaluating the integral, or are you just essentially plugging in x equals 0 for your boundary condition?
The domain of integration in 1D is a point. And so I just plug in the point. So the boundary is a point, 0 and L. So there is no integration, right? The only reason, the reason I wrote it down in this more abstract form was so that I could introduce you to this notation here.
I see. Okay, thank you.
Okay, great. Let's go about differentiating this guy and see what pops out. So the question you may have, well, what are the equations that I'm solving for? So I'm going to go through all the machinery that may have seemed mysterious before, and it's going to serve a very important kind of practical purpose now. So let me erase here. Okay, so let's go ahead and figure out how to do this. So we have this guy here, pi. It's a function of u and lambda, and I want to take the derivative. So let's denote the derivative by big D, and that derivative is defined to be d pi d epsilon u plus epsilon delta u lambda epsilon equal to 0. We want to set that whole thing equal to 0. That's our first equation. That's going to find the minimum with respect to the first parameter u, And then we have to do, maybe we can denote this by a little subscript u so that we know what we're doing, right? It's a multivariable problem, right? So we have to take derivatives with respect, so this derivative is with respect to u holding lambda constant, and then the next one is going to be with respect to lambda holding u constant. So d lambda y u lambda d epsilon y u lambda plus epsilon delta lambda epsilon equal to 0 is equal to 0. Okay, so there's going to be two equations in our weak form. One that governs the behavior of the displacement and one that governs the behavior of the force, lambda, required to enforce the displacement constraint u naught. So let's do this. Let's plug in everywhere we see, for this first equation here, everywhere we see u, we're going to plug in u plus epsilon delta u. So we end up with d pi d pi u is equal to 1/2 0 to L u plus epsilon delta u comma x. Let's assume that E and A are constants. They don't change with respect to x. And we end up with this again, u plus epsilon delta u comma x dx plus lambda u 0 plus epsilon delta u 0 minus u naught u epsilon delta u f dx. Then one more term, minus u at L plus epsilon delta u at L h sub L. Oh, I ran out of space there. Let's see. All right, and so what we're going to do is we're going to take this entire statement, we're going to differentiate it with respect to epsilon, and then we're going to set epsilon equal to 0. Oops, it's the edge of my pad, sorry. All right, so let's do the derivative first. The integral, we're assuming that it does not depend on the displacement because of our small displacement assumption. So this differential operator can pass no problem right in here in through the integrals. So let's write this down. And if you notice, one thing we can do to simplify and help you see what the derivative is, notice that we really have this guy squared. Okay, so epsilon is inside of a quadratic, so we have to do a chain rule. So the 2 is going to come down, 2 over 2, the integral 0 to L of u plus epsilon delta u And then we're going to get a, let's see, a delta U EA dx. Let me just stop there. Any questions on what I just did?
I have a quick question. So are we using the get-tau derivative, or are we using like a, I'm kind of curious about the purpose of the U plus epsilon delta U and the lambda R. If that makes sense.
This is sometimes called a Gateau derivative, and then under certain smoothness assumptions, you can call it a Fréchet derivative as well. In mechanics, this is just called a variational derivative, which means it's a derivative of a functional, which is the integral, with respect to a function, which is u. And so this is the exact analog of a directional derivative in multivariable calculus extended to functions.
Oh, okay, sweet.
So the direction is delta u in this case. It's not a vector, right? Because it's with respect to a function. So this is the direction in which we're looking for our solution.
Okay.
Okay, so let's keep going. Plus lambda. And let's see. The only thing that depends on epsilon is this delta u naught, right? So it's just delta u 0, sorry, not u naught. And then we get 0 to L of delta u f dx minus delta u L h sub L. Those cancel, and then we want to set epsilon equal to 0. And you should see now that what's happening here is that when you set epsilon equal to 0, it is removing the higher order parts of functions. So we had a quadratic here, which means that it has some epsilon piece that survives differentiation. But when we let the limit go to 0, this guy goes to 0. And so this whole thing goes away. Everywhere else, there's no epsilon, so we're done. So this is our final answer, 0 to L, and this should look familiar to people, I would hope, is, maybe we'll switch this around, delta U, E, A, U, dx, plus lambda, delta U, 0, minus 0 to L, delta U f dx minus delta U L h sub L. And so what this derivative is that this, for it to be the derivative, it has to work for all. If you go back and look at the definition of a Gateau derivative, for it to exist, it has to exist in all search directions delta U. So this is our Gateau derivative right here for U. And this is what we call our weak form. Okay, this is our weak form. This is where the finite element method begins, is from this first equation. Okay, so this guy has to be equal to 0. That's what we want. We're looking for a minimum, right? For all delta U. We haven't specified function spaces yet. We'll go back and talk about that in a minute. Let's just say that it's going to come from some function space V. Okay, and then U also is going to come from, let's say, the same space. Okay, so there's our first guy. Our second guy is a lot simpler. So if we go back to our equation, there's only one term, this term right here, that has lambda in it. Everything else does not depend on lambda. So when you take the derivative, they're all going to be 0. They're constant with respect to lambda. So if I clean this guy up a little bit, we're going to replace this with lambda plus epsilon delta lambda in here. And then, so this guy, maybe I'll just move this up so that we don't have to rewrite everything, is nothing more than d epsilon of lambda plus epsilon delta lambda u at 0 minus u naught. And then epsilon goes to 0. So the only thing that survives here, this is from the perspective of this derivative, this differential operator, this is a constant. And so this is just some constant plus something that depends on epsilon. So if you run this through quickly, you're going to get delta lambda. I guess these are all evaluated at 0, aren't they? Oh, and then I ran out of space here. Let me. For all delta lambda. Okay, so now we're done, and we have this equation here. This is our weak form now for our finite element problem. This guy and this guy. So if you want to restate, let's call this maybe equation star, call this equation double star. What we want to do is we want to find u in some appropriate function space. Lambda, normally you would find it in a function space, but remember, it's just a number, right? So we're just looking for something in the real numbers here, such that star equals 0, double star equals 0 for all delta u in V and delta lambda in the reals. Okay, this is our weak form for this given problem. All right, let me field some questions. Please speak up. I know this was not clear to everybody, so let's take an opportunity to talk through it.
Yeah, Dr. Scott, I had one question where you threw in the lambda at 0. I just didn't see where we got from lambda to lambda evaluated at 0 when we were going over the second equation.
The second equation, this was written wrong. It's supposed to be, let's see, lambda at 0. This is evaluated. Now I should have put lambda at 0 all along.
Okay.
Yeah. Okay, any other questions?
So you have u of 0 and you have minus u naught. Your u is a function of x along your beam. When you say u naught and you have u of 0, what is the difference between those two?
This is actually a function of x. This is just a given number. So what we're saying is this Lagrange multiplier, we're going to solve for the force required to make sure that our function that we solve for, our displacement evaluated at the left endpoint, is equal to this displacement value, u naught.
Okay. So u naught was a constant we put in way at the beginning.
That's correct.
Okay.
Okay, so that's our weak form. Now, let's talk about function spaces. If we go back, let's see, this is, sorry, these are comma x's in here. Forgot that as well. Anyway, little typos here and there. So what space, what function space should V be in order for these integrals to make sense? This is why we talked at length about function spaces, because it dictates where we look for our functions, our solutions. So if I just set V equal to L2 over from 0 to L, would that be okay?
I'm gonna say no. Reading your lecture notes, V was always a subset of L2. So
Yeah, a subset, or let's just say, okay, let's say it's a subset. That's fine. Is even that okay? Look at this integral. This integral needs to make sense. L2 just means what? The function's in L2 if that function, just the function itself integrated from 0 to L is less than infinity. But it doesn't say if function's in L2, it doesn't mean that this can't happen. You see the derivatives here? All that L2 does is it controls the value of the function, right? It says the area has to be finite underneath the integrand. But that's not enough here. We have to control not only the function values, but also the derivatives. If we picked a function out of L2 where the first derivative, its integral was infinity, would that even make any sense anymore? It wouldn't even be a well-defined problem. And so what we do is we say, well, in fact, that's not what we want. What we want is H1. Remember, H1 is the Sobolev space where f plus f comma x has to be controlled. And that's why we introduced H1. So U, we're going to say it has to be an H1, and that's a classical space for second order differential operators, right? I mean, shouldn't be a huge surprise that that's an H1, since that's what everybody uses for every finite element problem, basically. So that's H1. Lambda doesn't even have to come from a function space. It's just a constant value. We're just going to solve for lambda directly. In the future, though, these will be spaces because we'll be in multiple dimensions. So there you go. That's it in terms of the function spaces. Any questions on that? I get a sense that, well, I don't know what I sense. I can't tell on Zoom. I have no idea what people are thinking. In the classroom, you can tell what people are thinking, but not on Zoom.
I think what I sense is it's been a while since we've talked about the function spaces, and so we all need to remember it. I at least need to.
Okay. Yeah, so what this indicates to everybody is, oh, I should go read that section again. All right, good. Let's move on.
Mike, I had a quick question. So this was a specific example or a specific problem that we solved for to find the weak solution. And so I assume that every time that you solve for the weak solution, what you also need to do, and what I'm getting here, is that you need to reassess what space U lies in to, I guess, finish out your problem.
That's exactly right. So
Okay.
what we've done is we've taken the variational derivative. You have to look at the integrals and make sure that they will make sense. If you pick L2, that's not going to make sense because these derivatives could blow up. There's functions in L2 where that happens. And so you go through and you look at everything and make sure that you pick a space where everything makes sense. That's correct. Okay, so let's move on. Now, as an engineer, you look at this, all this scribble on the here, and let me ask you the question, what are the actual equations that we're solving? Can you tell? Can you tell what the actual equations are? So we started from potential energy, Everything is an integral form. Take a variational derivative. Everything is an integral form. But as an engineer or a mathematician or anybody, it may be nice to know if I have enough test functions, right? What are the pointwise satisfied equations emanating from this weak form? In other words, what I'm saying is, what is the strong form corresponding to this weak form? If I can solve for the strong form, that will actually tell me exactly what equations I'm solving. And that's extremely important.
Well, you're solving for the strain at every point in that structure.
Well,
Is that what you're getting at?
Well, it's hard to tell. I can't tell by look. What I'm saying is, in order, you can never take a weak form without solve. I would always solve for the strong form corresponding to your weak form, because that will actually tell you the equations that you're solving for. And we're going to do that next. And what you'll see is, they're called the Euler-Lagrange equations, but it's also called the strong form. When we do that, when I write down the strong form, every engineer that's listening to me is going to be like, oh, that's like what I learned in my introductory mechanics of materials course. But you can't discern that just by looking at these integral equations. And so what happens in finite elements, and that's very important, is that if you postulate a weak form and it has maybe some extra terms that are enforcing this or that or the other, you should always, it's good practice to derive the strong form corresponding to the weak form so that you know exactly what equations you're solving. And don't have time to do that today, but we'll pick that up on either Friday or Monday. And I'll derive the strong form, and then we'll discretize with respect to both the CAD geometry as well as an auxiliary geometry that we'll leverage with splines. So I'll stick around for another 5 or 10 minutes, but I'm done lecturing for the day. Happy to field any more questions. Is there any more questions?
Well, I guess if you go back to where you were defining your equation, I don't know if you can because you're bored, you delete it. But when we were defining the picture of the beam, right, and you were putting in there U, what did you have U represent on that beam?
It's the transverse displacement as a function of x.
Okay.
Yeah, it's just an axial rod that's being either compressed or stretched along the x-axis.
So the axial displacement, not the transverse, right?
Yep, we're assuming that might have been a good question to ask, but we're assuming that this rod is thin enough. Well, actually, it doesn't even matter because the force only acts in the x direction and it's through the centroid. So there's only transverse displacement.
You're saying transverse. I think you mean axial.
Sorry, yeah, I mean axial.
Okay.
Axial.
So, Dr. Scott, I'm still a little confused on the difference between a derivative and like a normal directional derivative, because as far as I remember from my multivariable calculus class, like you took directional derivatives of functions generally. They're multivariable functions. So I guess what is I'm just confused on what the need is.
You're taking derivatives with respect to multivariable functionals. That's what we're doing.
Oh, okay.
So integral is a function of the function, right? So we have a multivariable, and so it's not a vector like a vector direction in Rn. It's actually with respect to some delta, which is some variation in a function.
Okay.
Have you not seen that yet, Phil?
I'm sorry, I didn't, if that was a question for me, I didn't hear what anybody said.
Have you not seen that before? Just the percent.
The Gattau derivative? I mean, besides going over it in mathematical preliminaries, I haven't seen it before
Okay.
this class.
Now you're part of the cool club.
Yeah.
So we got some BYU students still on. So we're posting solutions. I hope that's helpful. Has that been helpful to look at like what you did wrong or did right?
Yeah, that's been pretty helpful.
You're gonna have to mute Kaylin because there's a lot of like crunchy static coming from you.
So yeah, the solutions have been very helpful. Thank you.
Okay. Okay. Well, I don't think there's anything else. You done?
So I sent an email to the teaching assistants. They have office hours indicated. I'd like to try to brainstorm a better way to get in touch with individuals at specific times. I don't have time to kind of ping someone and say, hey, let's try to meet up at some point in time. I've got my schedule pretty booked, but I can put on my calendar specific times. So I tried to do that for their office hours, but I haven't been able to catch them even during their office hours. So maybe we can discuss some way that specific times in the week and I can just set aside that time to come with questions on the homework.
Eric, how are you trying to catch us during office hours?
What was that?
How are you attempting to catch us during office hours?
I jump onto the Zoom meeting, and then if you're not there, I try to email.
So we've got specific Zoom meetings that are for each of the TAs. I can send you those links.
Yeah, I have them, and I jumped on them.
Okay.
Like just today, I jumped on the one that was today this morning, and nobody was there.
Okay, I think that was because Kyle was out with a fever.
Oh, okay.
In general, that should work. It's usually helpful if you send an email before, like, I'm not sure that we're always just sitting there waiting for someone to come, but if we know someone's coming, then we do have that time set aside. So probably
Okay.
if you email before you jump on, you'll probably, and assuming that people don't have fevers or something, then you should be able to reach us at those
Okay.
times.
Sounds good.
And Eric, you have my cell phone number. If you text me that you need to talk to a TA, I'll make sure that one of the TAs is there.
Okay. Yeah, I'm gonna try to make it to the office hours. So that, I mean, I have it on my calendar, so I'll try to do that. I think we have another one on Thursday.
Yeah, I think that's Chris.
Okay, I'll be there. Thanks.
Sorry about that, Eric.
All right. I'll see everybody later.